Introduction to Microprocessors and Embedded Systems Development, Lecture 3, Chapter 6 and 4. Hello, everyone. In this lecture, we will talk about some arithmetic and logical instruction and simple branches and loops in assembly language. So here is the outline. We'll talk about addition and subtraction, which I already mentioned in the previous lecture, but we are going to go into the details of these operations in assembly. Multiplication and division, some logical instructions like masking and compare, shift and rotate, which are important instructions in arithmetical and logical unit. Data serialization, BCD, PAC BCD, and ASCII conversions will be covered in an arithmetic logic part. And then we also get into the details of some function calls, the loops and the branches, which will be the second part of this lecture. So if we just revise what we have done in lecture 2 about arithmetic instructions, addition of unsigned numbers, we have used an instruction add, where we have got RD and RR. So two registers that we use, and the command for this is RD equals RD plus RR. Now, this instruction adds the resource, which is RR, to the destination and stores the result in RD. So that's what it means. And in the end, it could change any of the instructions, any of the flags like 0, carry, negative, overflow, half carry, or sign bits of the status registers as we have done it. And it does not support the immediate, so you cannot add a constant to the register. So we don't have add I instruction in AVR assembly. So here's a simple example, which is similar to what we have done in the previous lecture. Show how the flag register is affected by the following instruction. So we have got 0 hex F5 and 0 hex 0B. Now, these are the two data that we have stored in R21 and R22, and we have to perform the R21, R22 addition. So what will happen is we have to add these two together. Now, if you want, we can go bit by bit and check what will happen. So F is 1, 1, 1, 1, and 5 is 0, 1, 0, 1. And 0 is 0, 0, 0, 0, and B is 1, 0, 1, 1. Then when we do the addition, 1, 1, 0, carry 1, 0, carry 1, 0, carry 1, 0, carry 1. That creates a half carry. This is half carry, so H flag is 1. And then I'll carry on 1, 1, 0, carry 1, 0, carry 1, 0, carry 1, and 0, carry 1. So we also have a carry flag set. So carry is also 1, and as 8-bit output is 0, 0 flag is also 1. So we have done this, and I'm just revising it quickly so that we can understand. And another add instruction that we generally use is called ADC. Now, you might ask, what's the difference between add and ADC? It's used for an addition of 16-bit numbers. So addition of 16-bit numbers. What do we mean by that? So when we are adding two 16-bit data operands, propagation of a carry from the lower byte to the higher byte is concerned, and this is actually called a multi-byte addition. So for example, it's actually the same approach. There's nothing different over here. ADC and we have got the instruction RD and RC. So if you write the comment for it, this looks like RD is equals RD plus RC, or the resource, whatever you want to call it. Let's make it a resource so it will be easier to understand. So RR and RR plus the carry bit. Okay, now for example, we have got 16-bit, two 16-bit numbers. Let's say 3CE7 hex and 3B8D hex. Now we have got, let's say, the registers which we have stored these values in. So R1 is equals, let's say, the first byte, which is 8D. R2 is 3B. And then R3 is E7. And R4 is 3C. So we are storing 8 bits of data into one of those registers. So in order to perform an operation, so we have to perform the addition operation. So this is going to be like 3C E7 and 3B8D. It looks like it. Maybe I have to write closer so that I can have enough space. 3CE7 and 3B8D. So 0, 0, 1, 1, 1, 1, 0, 0, 1, 1, 1, 0, and 0, 1, 1, 1. Okay, so this is a typical addition, bit by bit, if you want to show it. If you want, you can do an hexadecimal addition. That's also valid. 0, 0, 1, 1, 1, 0, 1, 1, 1, 0, 0, 0, and D is 1, 1, 0, 1. Right, so this is the lower bytes. I'm just putting, and this is the higher byte. So I'll say LB and HB. Okay, so when we do the addition, 1, 1, 0, carry 1, 0, carry 1, 1, carry 1, and then 1, 1, 0, carry 1. That is 1, 1, 1, 1, 1, 0, and then carry 1. As you can see, from lower byte to higher byte, we have got a carry. Okay, so this is 4, this is 7, and we have got a carry, which we need to place it as a carry bit over here. Then it carries on 1, 1, 0, carry 1, 0, carry 1, 1, carry 1. And then that will be 1, and then carry 1, 1, carry 1, 1, carry 1, 1, and 0. And this part is 7. I made a mistake, I guess, over there. That should be 1, 1, 0. Oops. Let's fix that out. So 0, 0, and 1 over there. And this will be 8 and 7. So 7, 8, 7, 4. Now, this is actually, I can show it from your slides. Now, what is happening is it adds R1 and R3 first, okay, as an operation wise, and then it adds R2 and R4, but we also have the carry, so we have to add that one in as well. So that's why we use ADC in the second instruction. So R1 and R3 is added and stored in R3. So E7 plus 8D, which is 74, and there's a carry. And then this carry is stored in the status register, by the way. And then we perform R2 plus R4, which is these two. And we also have the carry, adding to upper byte. So 3C plus 3B plus 1 is 7, 8 hex. Okay, so another instruction that we are using with the add function is add immediate with word. What do we mean by that? Add immediate to word. I'll write here. This is the only immediate that we can use in add instruction. Now, add immediate to word is an instruction like rd plus 1 rd, and we have got a constant k. Now, in this instruction, it adds an immediate value in the range of 0 to 63. So k is in the range 0 to 63. Okay. And it adds to a register pair. So which register pairs we can use is already specified in AVR. So this D is actually can be register 24, 26, 28, or 30. So when we say register pair, it's actually R24 and R25. So RD plus 1 is 25, or R26, oops, and R27, R28 and R29, or R30 and R31. So these are the register pairs that we can use add immediate with word. So for example, write a program to add 18 to 2917 hex and store the result in R25. So that means we are going to store these values with, I'll write it over here again just to show it. LDI R25, which is RD plus 1, will have the value of higher byte, which is 0 hex 29. Okay, so I'll write the comment. Its comment is written over there, so I'm not going to rewrite it. LDI R24, then we will have the low byte of it, 0 hex 17. Now, what we can do is we can use add immediate with word. We have to specify that R25, R24, the register pairs that we need to use, and that will be stored. And what will be added? It will be added 0 hex 18. Okay, so the operation is the result will be stored in R24, R25. It's actually stored in R24, R25 as it's 16 bits. And this is going to be like 29, 17 plus 18. And that will be, again, R25, R24. And it will be stored. So 5, 35, 29 hex. This will be stored. Okay, so 3 adds instructions that we use generally in assembly language. We also have subtract instruction. Subtract is similar to add. Subtract unsigned, subtract with borrow actually. So if we have a borrow from the previous 8 bits, we can borrow that, not in this one. Sub I is in sub instruction, we can use subtract immediate. So if we have a constant, we can subtract directly with the register value, and subtract immediate with borrow is also valid. So another version of the carry, and subtract immediate with word is similar to add immediate with word. Okay, one thing that students need to understand is how to perform hexadecimal operations. So hexadecimal addition and subtraction. I mean, you can convert it to bit by bit and find it in binary and then convert it to hexadecimal. There's a straightforward as well over here. So show how the flag register is affected. This is a typical subtract operation. 3f minus 23. Now f is what? F is 15. So 15 minus 3 is, f is 14. Okay, so, sorry, f is 15. 15 minus 23, which is going to be in the 2's complement form. Okay, that's why it's not 3. It's in the 2's complement form of 3 over there. Okay, and when we subtract those, what we are going to get is 12. 15 minus 3 will give us 12, which is 110, which is equivalent to C. And this part is 3 and the 2's complement of 2, which is going to be 3 minus 2, 1. And also we have got an extra bit that we need to discard, if you do remember from logic design. So we have got the value stored in the register R21. So any flags, carry flag is 0 as we are not borrowing. Result is positive. 1C is positive as 3F is bigger than 23, and there are no zeros in the 8 bits. So subtract with borrow instruction. Now subtract with borrow instruction, it's similar to the carry, but if you are borrowing from the upper higher bits or byte, that will be reflected into the C. So if you do the operation over here, subtract 26, 28. So we have got two values, 2762 and 12962, 96, sorry. R26 has got 62 and R27 has got 27 hex. Okay, R28 got 96 and R29 got 12. So these are all stored in one register, and the first operation is subtract 96 from 62, which is R28 and R26. So subtract R28, R26. Now 62 minus 96 is CCH, which is CC in hex, but there's a carry which we need to borrow in order to perform that subtraction from here. So that's why we have got the borrow equals to 1, and this means we also have a negative flag to be raised. And then we subtract R29 from R27, and of course we need to have the borrow, and this will give us the hex value 14 hex. You can try these by yourself if you want. So we use subtract with carry if we have got a two 16-bit numbers. Subtract immediate, it's immediate constant, which is between 0 to 255, can be subtracted from any register. So write a program to subtract 18 hex from 29 hex and store the result in R29. So let's initialize 29 to R21 and then use sub I subtract 18 hex from R21, and that will give us 11 hex. Subtract immediate with word. Again, we can use a register pair like we have done it in the other. The K can be between 0 and 63. And we have got two register pairs over there, and we can store the values in those when we perform the subtract operation. So once again, R25 will have the higher byte, R24 will have the lower byte, and then we use subtract immediate with word and subtract the immediate value 18 from 2917 hex, and this is going to be 28FF So typical subtract and add operations can be performed using these instructions. Multiplication, they are generally performed in 2 cycles, and we have got 3 instructions for multiplication. Multiplication for the unsigned is just multiply 2 registers, and then R1, R0 will have the value of the multiplication. So you always have 2 registers, which are 16 bits that you can have the result in. And they are always stored in R1 and R0 for multiplication instruction. Be careful. Multiplication with the signed numbers is multiplication S. Again, the same instruction, and it will be stored in R1 and R0. Once again, it's going to be 16-bit data. Only thing that you need to take care over here, D, which is the destination register, is between 16 and 31. Okay, and multiplication for unsigned and the signed. So signed, unsigned is there. And again, the registers are R1 and R0 will be used to store the results. And it can be again between 16 and 23 over here. So LDI R23, if you want to do a multiplication, LDI R23 has got hex 25, R24 has got hex 65, and then we do an unsigned multiplication of those, and the result is not stored in R23, it's stored in register 1 and register 0. Division, we don't have a specific division instruction in AVR assembly, but you can use a typical subtract instructions in order to do a division. So it's like a repeated subtraction. You just need to initialize numerator, denominator, and the quotient, which is 0 at the beginning. Then typical division can be followed, incrementing the quotient, subtracting denominator from the numerator. You can initialize this as a definition, and then check if it is 0, decrement the quotient, and so on. So these are simple instructions that in order to do a division operation. So we load the numbers, we clear the quotient, we increment the quotient, and we subtract. We check if it is 0, it's not, repeat it, increment the quotient, and so on. So it's going to loop over here, subtract, increment, until you reach to the end. And then we decrement the quotient. So in arithmetic logic unit, another important thing is logical instructions. So logical instructions that we use are AND, OR, XOR, complement, and negate. Complement is 1's complement, negate is 2's complement. And again, it's between the register pairs. Okay, they have got an immediate version and but you have to use the registers between 16 to 31. In these ones, you don't need to. You can use any of the GPR registers, but if you are using immediate instruction, it has to be between 16 and 31. And same applies for OR. And XOR, it doesn't have an immediate, but you can do an exclusive OR, which is an odd function, by using RD XOR RR. So the complement just gives complements or inverts each bit of the register, and negate, it takes the 2's complement, which we can use in signed binary numbers. Now, generally, we are using AND instruction to clear the specific bits, because when you are ending something with 0, it's actually going to end up with 0. And we are using OR in order to set specific bits. So if you are ORing something with 1, it's going to be 1. So for example, we have got LDI R20, which is 0 hex 35, and I and with immediate, so R20 0 hex 0F. Now what will happen? 0 hex 35 is 0, 0, 1, 1 and 0, 1, 0, 1. Okay, and R20 is, in this case, ended with 0 hex 0F. So this is 0 and this is going to be 1. So when we are ending these together, this part, as it is all ones, it's going to be set it as they are. But as these are going to be ended with 0, these are all going to be 0. So we can set the lower 4 bit to be 0, 1, 0, 1 and higher 4 bits to be 0. This is called bitwise AND. Okay, and bitwise OR is similar. Let's say LDI R20, 0 hex 04, or I R20, 0 hex 30. Now, 0 hex 04 is 0, 0, 0, 0, 0, 1, 0, 0. Now, 30 is 0, 0, 1, 1 and 0, 0, 0, 0. Now, we can actually set these bits to be 3 in this case, because this part is not going to change, but this part is going to be 3. So we can set actually the bits by using OR I, and this is known as bitwise OR operation, which is quite useful in logic instructions. Okay, by using these instructions, and we have got the status register and the flags in the status register, we can easily do branches, like we have mentioned in the previous lecture. And also, we can use compare instruction. So it's actually do a comparison between the 2 registers. So only for flag set, it doesn't perform any arithmetic operation. It just compares 2 of the registers, and it sets the flag in the status register. So the compare instructions can use one of these branches. If they are equal, branch equal. So that means if z equals 1, so that means 0 flag is 1. Branch not equal, that means z equals 0. A branch if same or higher, if carry is 0. Branch is if lower, if carry is 1. Less than, which ports the signed ones, if sign bit is 1, and greater than if sign bit is 0. Okay, so you can use these branches, and we can check for the flags and jump to somewhere else in the program. And we also have BRVC, which is used to branch when overflow is clear to 0, or branch when overflow is set to 1, VS. Okay, these two can also be used. Right, so another important instruction that we use in arithmetic logic unit is rotate instruction. So rotate instruction, ROR, RD. So you specify the register and you rotate. Now rotate, as you can see from the diagram, we have got an 8-bit data, MSB to LSB, okay? And we also have the carry bit from the status register. Now, when we are rotating right, we are actually going this way, and the least significant bit goes into the carry flag, and then from the carry flag, it returns back and comes in. So in rotate, whatever you have got in carry flag will fit back in. So let's try this example, which is 0, 0, 1, 0, 0, 1, 1, 0. Okay? Now, what will happen with this? So, as the program says, clear carry first. So we make the carry flag to be 0. Okay? So at the beginning, it is 0, and this is our data. Then we initialize our data, hex 26. We have got it in the register. Rotate right. So if you rotate once, I'll keep this one over here and the carry bit. We have to do 3 rotates, so let's have 3 of those to symbolize it. And then if we rotate 1, this is going to be coming over here, okay? And this one will fit in to here. Okay, so 0, 0, 0, 1, then 0, 0, 1, 1. It's rotated once. Then we repeat this again. This 1 will be over here. And this 0 will be fed back in. So 0, 0, 0, 0, 1, 0, 0, 1. And then this one will be over here, and this one will be fed back in. So 1, 0, 0, 0, 0, 1, 0, 0. And it goes like that if you have more rotate instructions. So this is what you are going to get as an output based on your rotation. We can also do the similar with the rotate left. So it's just a mirrored version of it. So the carry is going to be on the other side where we are rotating from least significant to most significant. And then the carry will be fed back into the least significant bit. And you can easily rotate them to any direction.